Okay, I have uploaded last year paper to the LMS. Okay, actually that is a 3 credit module. Okay, so your module is 1 credit. Okay, so you have to do only 2 questions. Okay, so I just highlight you to do some questions. Okay, we will go to that paper. Okay, this is the paper. Okay. So you there is a password. That password is this code number. Okay, EEE103. EEE103. That is the password. Okay, you can see it. No, this is the password. Then you can open the file. Okay. So actually, this question paper has around 4 questions. Okay, but you know that our module is a 1 credit module. Okay. So basically, we are mainly focusing on, okay, basically uh, our module is 1 credit module. Okay, 1 credit module. Okay, so there are only 15 hours we need to study active. Okay, lectures hours are 15 hours only. Okay, so basically you will have 2 questions, question 1 and question 2. Okay, question 1 and question 2. So 1 question will get 50 marks. Okay. So this is a 1 hour paper. Okay. This is a 1 hour open book paper. Okay. This is 1 hour open book. Okay. So no need. Uh, it is not much difficult. Okay. So there will be 2 questions. Okay. The all question will be based on RC. That means resistor, capacitor, RL, resistor, inductor, and RLC, resistor, inductor, capacitor. Okay. These type of three, all the question 1 and question 2 will be based on these type of circuits only. Okay, RC circuit, RL circuit, and RLC circuit. Okay, so so you will have to study both transient and steady state. Transient state, we have discussed these things, transient state and steady state. Okay, steady state. Actually, steady state is very easy. You know that. In steady state, you can consider capacitor C as a open circuit one. Okay, open circuit one. Okay. So this is basically when the DC source are available. Okay, when the DC source are available. Okay, if the DC source are there. Okay, transient state and steady states can be have in this RC, RL, RLC network. Okay. So at the steady state, the capacitor will be open circuit and inductor will be short circuited. Okay. Short circuited. So basically, that means at the steady state, that is only a, resistive network. Okay. It is only a resistive network. So you can apply Kirchhoff law and Ohm's law and find the voltage and current. Okay. So that is very easy. Steady state. Okay. ඒක තේරුණාද? Steady state වෙලාවේදී හැම කැප් එකක්ම open circuit කරන්න. Inductor short circuit කරන්න. Short circuit කරපුවාම එන්නේ resistor විතරයි. එතකොට resistor circuit එකේ Kirchhoff law, Ohm's law දාලා ඔය කට්ටියට current voltage හොයන්න තියෙනවා. A level වල කරා වගේ. හරි. එතකොට මේ open circuit, short circuit වුණාම තව ටිකක් ලේසි වෙනවා circuit. හරි. So steady state is not difficult. Okay. And you need to focus in on transient state. Okay. So you know that at the transient state, the capacitor has a equation for voltages and current, and inductor also have the equation for voltages and current. Okay, so you basically need to know this equation. Okay, so if you want to analyze the circuit at the transient state, you need to know this voltage and current relationship. Okay, so I think you can remember that. Okay, we have discussed it many times. Okay, අපි classroom වල සෑහෙන්න කතා කරා. Okay, so if you consider capacitor, okay, you know that the charging voltage is somewhat like this. Okay, so this is the maximum voltage it can be achieved. Okay, and the current curve will be like this. Okay, okay. So the capacitor voltage, you can write the equation for the voltage, you can write it as 1 over C integrate IT dt. This is the current through the capacitor. This is the current through the capacitor and this is the voltage across the capacitor. This is current through the capacitor and voltage across the capacitor. Capacitor voltage and capacitor current. Okay. The current is through the capacitor. Voltage is across the capacitor. හරි මේ තියෙන capacitor එකේ අතර voltage එක සහ current එක. හරි ඒක ඇතුලෙන් යන current එක. හරි plus there may be an initial voltage V naught or something. Okay, so this may be within a time period. Okay, this may be the 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 integration will be within a time period. Okay, so you have to identify what is the time period, the integration. Okay, the same way you can write the capacitor current as C dVt dt in this way. Okay, so this is the capacitor voltage and capacitor current. Okay, and if you consider inductor, okay, if you consider inductor, okay, it is vice versa. Okay, the voltage curve is like this. Voltage curve is just like a current curve of a capacitor. This is the voltage curve of the inductor, and current curve of the inductor is exactly identical to the voltage curve of a capacitor. හරි එතකොට ඉන්ඩක්ටර් එකේ voltage curve එක capacitor එකේ current curve එක වගේ ඉන්ඩක්ටර් එකේ current curve එක capacitor එකේ voltage curve එක වගේ ඒ දෙක වෙනස් වෙලා. එතකොට මේ equation උත් අනිත් පැත්ත ගහනවා. හරි so the equation also will be identical, but other side voltage and current will be interchanged. Okay, so we can write inductor current IT. This is the inductor current through the inductor. Okay, current through the inductor. This is that the transient state. Transient state means this state. Okay, this is the transient state. This is the transient state and this is the steady state. Okay, this is the steady state. So here also, this is the transient state. Okay, at the transient state, current is flowing. Okay, at the steady state, the current, there will be a maximum current. That means it is a short circuit. The current will be high. And in this case, current will be 0. That means the capacitor is open circuit. So that is why I asked you to remember at the steady state, capacitor is as open circuit, inductor just like short circuit. හරි තේරෙනව නේද නේ? දැන් මෙන්න මේ current එක තියෙන වෙලාව තමයි දැන් මෙන්න මේ voltage එකයි current එකයි වෙනස් වෙන වෙලාව තමයි transient state එක. steady state එක කියන්නේ ඒවා නියතව තියෙන වෙලාව. එතකොට capacitor එක ගත්තාම steady state එකේදී current එක බිඳුවයි. ඒ කියන්නේ ඌ open circuit වගේ. inductor එක ගත්තාම steady state එක ඒ කියන්නේ current එක නියත වෙන්නේ. හරි? මෙන්න මේ අවස්ථාවේදී එතකොට current එකට high value එකක් තියෙනවා voltage එක බිඳුව වෙලා හැබැයි. හරි steady state එකේ කියන්නේ voltage එක බිඳුවයි කියන්නේ inductor එක open circuit. හරි එතකොට steady state එකේ capacitor එක open circuit inductor එක short circuit. මම ඉස්සෙල්ලා පාර වැරදියට දන්නේ නැහැ කිව්වේ. හරි voltage එක බිඳුවයි කියන්නේ මෙයා short circuit. current එක high කියන්නේ inductor එක short circuit කියන එක. හරි. right. එතකොට we can write the current as in the same way, okay, 1 over L. Now this C is the capacitance measured in farad. L is the inductance measured in Henry. You know that, okay? So 1 over L integration within a t time. Now, in this case, this is IT dt, but here it should be VT dt. The VT is the inductor voltage across the inductor voltage. Plus, there will be a initial current. Okay, there will be a initial current. Okay. In this case, it has initial voltage, but in this way, inductor will have initial current like this. Okay. And the voltage of the inductor can be written as L di dt. Okay. So these are the transient state equation. Okay. So you need to understand this equation. That is very important. Okay. You need to understand and you need to know how to apply this. Okay. At the transient state. Okay. For the steady state, you no need to apply this equation. Okay. So what I again tell you is at the steady state, the circuit will be the cap will be open circuit, inductor will be short circuited. Okay. So these are the equation valid for the transient state. Okay. So this is at the transient state. Transient state. Okay. When the DC source is there. When the DC source is there. Okay. So actually in your paper, around 65, not 65, around 70 mark, 70 to 75 marks will be based on transient state. Transient state. That means you need to know this equation very well. Okay. මේ equation හොඳට දැනගන්න ඕන, apply කරන්න දැනගන්න ඕන. මේවා එතකොට apply කරලා තියෙනවා අර මම ඔකටට දුන්න PowerPoints වල apply කරලා තියෙනවා. උදේ සර්ගේ අපි ඒවා class වලත් හැදුවා. කට්ටිය ගොඩක් class වලට ආවේ නැහැ. එතකොට උදේ සර්ගේ වීඩියෝ වල මම දාලා තියෙනවා. ඒ වගේ එයා මේවා විසඳනවා. හරි? එතකොට ඔය කට්ටිය ඒ ගණන් ටික හදන්න පුළුවන් වෙනවා. හරි? basically PowerPoint වල තියෙන මෙන්න මේ RC RL RLC ගණන් ටික. Okay? So there may be some question related with op-amps, diode, okay? Op-amps, diode. You no need to go through these circuits, okay? Because this is a one credit module. So we are strictly focusing on this RC, RL and RLC network, okay? So you no need to go for the circuits with other components, okay? So you have to do that questions, the PowerPoint questions, and the lectures are also there. Okay, please go through it within today. Okay. Okay. So as I told you, 70 to 75 marks will be based on transient state. Okay. And steady state is very easy, okay? Steady state is very easy, so you will get around 10 to 15 marks from steady state, okay? හරි. මේ steady state එක ලේසි. ඉතින් ඒක O level මේ A level ගණන් වගේ A level තරම්වත් අමාරු නෑ නිකන්. මොකද cap තියෙන ඒවා open වෙනවා, inductor තියෙන ඒවා short වෙනවා. එතකොට ඔය resistor එකක් දෙකක් තියෙන circuit එකක් එන්නේ. හරි? එතකොට ඒකකට ලකුණු ඔකට්ටියට හම්බෙන්නේ මේ වගේ කෑල්ල, ඒ කියන්නේ steady state එකෙන් ලකුණු 10ක් 15ක් වගේ ගන්න පුළුවන්. හරි? So you can get around 10 to 15 marks, okay? And maybe I think only 2 or 3 people's are there when we do that part, okay? There is a part we can use Laplace transform, okay, for the circuit analysis. That is actually S domain, okay? So we are using this S domain, okay? So these are time domain. These analyses are time domain, okay? This transient analysis, state analysis, these all are in time domain, Okay, these are time domain analysis. හරි. equation ලියලා තියෙන්නේ time domain එකේ. හරි. මේ පේනවනේ මේ voltage වලට inductor වලට equation ලියලා තියෙන්නේ time domain එකේ. Uh, we can do this in S domain. S domain means that is a complex domain. Okay, I have explained these domains. Now we don't have much time. Okay, but I will tell how to solve the question. That is very easy. Using a Laplace transform, actually you can easily find the solution rather than using this transient state time domain equation. Okay, this Laplace transformation actually we use to make easy the analysis. Okay, so we can make easy the analysis rather than using the transient equation S domain. Okay? So I will do one question, then you can do that one. Okay, so don't worry if you haven't done this before. Okay, in our class also I think only 1 or 2 hour we have done this. Okay, we are focusing on, we were focusing on this Laplace transform analysis. Okay, the main analysis, the many parts we have done in the time domain. Okay, so this is S domain analysis. Okay, this is S domain analysis, and you will get around 15 to 20 marks, not much marks. Okay, 15 to 20 marks. Okay, so this is how your marks composition. Okay, for the transient state, you will get higher marks, around more than 70. For the steady state, around 10. For the Laplace transform, around 15. Okay, so that is how your mark composition. හරි, තේරුණානේ ඒකනේ? සාමාන්‍යයෙන් transient state එක කියන්නේ මෙන්න මේ time domain equation, මෙන්න මේ time domain equation පාවිච්චි කරලා ඔය කට්ටියට ලකුණු 70ක් 75ක් ගන්න තියෙනවා මේ paper එකේ. ඊට පස්සේ මේ steady state එකේ. හරි, එතකොට steady state එකේ මේ equation දාන්න ඕනේ Ohm's law, Kirchhoff law දාන්න තියෙන resistor වලට. resistor වල කියන්නේ V සමාන IR නේ, Ohm's law එකනේ. V equal IR. මේ I කියන එක වෙනස් වෙන්නේ නැහැ resistor වල. But in inductor and capacitor, this I is changing at the transient state. You can see it. The I is changing. Here the I is changing. Current is changing. And the voltage are also changing. The voltage are changing. But across the resistor, the current or voltage are not changing. Okay. So it is simply a Ohm's law if the resistor are there. Okay. But capacitor and inductor, in case of capacitor and inductor, you have to apply this transient equation. Okay. හරි. එතකොට ලකුණු 70ක් 75ක් තියෙන මෙන්න මේ transient state එකේ. එතකොට ලකුණු 10ක් 15ක් ඔය කට්ටියට ගන්න පුළුවන් මෙන්න මේ steady state එකෙන්. හරි. ඒකේ ලකුණු 10 15ක් මම ගයි කියලා හිතනවා කට්ටිය. මොකද ඔය කට්ටිය හැමෝම A level මේ physics pass වෙලා ආපු කට්ටිය නිසා. හරි. එතකොට ලකුණු 15ක් විතර වලට මේ S analysis එකෙන් ගත්ත හැකි. මම හිතන්නේ ඔය කට්ටිය අර දැන් lateral entry කට්ටියම already කරලා දෙනවා. ඒ Laplace එකෙන් ඔය control system වලට එහෙම අපි circuit මේ ඔල ඔය transfer function හොයන්නේ මේ Laplace transform පාවිච්චි කරලා. හරි. එතකොට මේකත් එච්චර අමාරු නෑ. මේකෙත් ඔය කට්ටිය ලකුණු 15ම ගන්න පුළුවන්. හරි. Okay. So this is the composition of your paper. Do you have any problem? මොන හරි ප්‍රශ්න තියෙනවද මේ ටිකේ? Okay, if not, we will move to the model paper. Okay, so the model paper, actually that is not a model paper, that is the last year paper. Okay, so second order calculation බලන්න ඕන. හරි. හැබැයි ඔය කට්ටිය differential equation solve කරන්න එපා. හරි. මම මෙතනදිම කියන්නම්. හරි. හරි. So when you are analyzing the circuit in the transient state, you can see that the integration and differentiation are there. හරි. දැන් transient state එකේ මේ අවකලන අනුකලන තියෙනවා. එතකොට ඒ වගේම තමයි equation එක ලියවෙන්නේ. හරි. ඔය කට්ටිය Kirchhoff law දාපුවම voltage එකට current එකට අවකලනයක් අනුකලනයක් ලියන්න ඕන. හරි. අපි බලමු දැන් ප්‍රශ්න එක. හරි. එතකොට ඔය කට්ටියට එන්නේ හුඟක් වෙලාවට transient state එකේදී at the transient state, the very often you will get a differential equation. Differential equation. Okay, differential equation. In the case of RC and RL, most probably these are first order differential equation. First order differential equation. Are it? When the RLC there, when the RLC circuits there, it can be a second order differential equation. Okay. So exactly, you have to deal with first order differential equation and second order differential equation. But don't worry, I do not need you to solve this. Okay, so that the solve in differential equation I am not expecting. Solving the differential equation I am not expecting. Okay, so uh, when you are doing the exam, don't take much time to solve the differential equation. The differential equation can be solved in many ways. Using most probably in this circuit, you can use a natural response and force response to solve this. And also maybe most probably you can use that variable separation method. I think you have learned these things, okay? Variable separation method, separated measure or something, separation method, okay? Most probably using this two method, you can solve this differential equation, but I am not expecting it, okay? If you have solved it, you will get around 2 or 3 marks, okay? For example, if there is the transient state question which have 10 marks, okay? So the 8 marks I will be allocated for the differential equation. Differential equation and the initial condition. You need to get the differential equation, correct differential equation, and you need to verify the initial condition. Initial condition means most probably this the capacitor voltage may be one initial condition and inductor current will be a initial condition. Okay, so that is very easy. Okay, so the differential equation and initial condition, if you have properly identified, then you will get around 8 marks, and only 2 marks will be there to solve in the differential equation. Okay, for the solve in the differential equation, you will get around 2 marks. Okay, if it is a 10 marks question, to get the correct differential equation and initial condition, you will have 8 marks. Solve it, you will have around 2 marks. Okay, so don't worry. Okay, so you can easily get the differential equation. Okay, we will do some question, you can understand. Okay, um, actually in our class we have done this. Yeah, maybe I told you that for the S domain, okay, so for the transient domain, okay, for the transient domain, you will have the DC source only, okay, the DC voltage source. Actually, I am not, I haven't included, as I can remember, the current source I haven't included, okay, current source I haven't included, okay, so only DC source will be there, that means battery, okay, DC battery will be there. And for the Laplace transformation, maybe as I can remember, I use sinusoidal signal. So that is easy, okay? Sinusoidal is easy when you are using the Laplace domain. Okay, when you are using the Laplace domain, sinusoidal signal will be easy. Okay, so I have used the sinusoidal uh, source for the Laplace question. Okay, okay, for the Laplace question. So I told you that there is a transient question, steady state is question. For both, DC voltage source will be there, DC source voltage. And for the Laplace transform question, it is around 20 mark, 15 to 20 marks. Okay, you are given a sinusoidal source, sinusoidal source. So that means there is a voltage, no, omega. Okay, so sinusoidal voltage will be easy, but it is not much affected. Okay, so So DC source, mainly you need to focus on DC source, not the sinusoidal source. When you are analyzing this transient and steady state. Okay. හරිනේ තේරුණානේ? අර ලප්ලාස් ට්‍රාන්ස්ෆෝම් එකට මම දාලා තියෙනවා DC AC source එකක්. ඒකේ වුණාට ගණන් ගන්න එපා. කොහොමදත් අපි අර S දාගෙන හදනකොට මොකොත් ගණන් ගන්නෑ. මම මේක කියන්නම් හදන හැටි. නිකම්ම හදන්න පුළුවන් අපිට ගාන. හැබැයි transient state steady state වලට RC RLC සහ RL network වලට ඔය කට්ටියට එන්නේ DC source එකක්. හරි? Okay. Now we will move to the paper. Okay. So this is the first question. Okay. And in your paper also, the first question will be exactly like this. Okay. So you will, so sometime maybe there can be different. Okay. For example, this may be a RLC network. Okay. I told you that RC, RLC and RL networks are there. Okay. So this can be a sometime maybe RC network or maybe with the DC source. Okay. So it may be with the DC source, RC circuit with the DC source. Okay. But the same way you have to solve this in the same way. Okay. I will get this Word version because I can directly copy the circuit. Okay. So for example, here so this kind of question you will get definitely. Okay. So this is very simple question. Okay. So sometime you will have a DC source sometime. Okay. Here. Okay. So for example, so here so this is actually discharging circuit. Okay. This is the discharging circuit. So this capacitor is work as a DC source. Okay. Okay, so it is discharging and you asked to find the capacitor. Okay, you asked to find the time. The voltage across the capacitor is 1 volt. Okay, so we will do this. Okay. Okay, how to do this? If I give you 5 minutes, just try to understand. Try to write the equation for this. Try to write that is very simple. Okay, that is very simple. Okay. Okay, side. Okay, now you are asked to find the you are asked to find the voltage. Okay, voltage. This voltage VT across the capacitor. Okay, voltage across the capacitor. Okay, so for this one, you need to use that transient state equation, time domain equation. Okay, so using that time domain equation, can you try to get the differential equation for this? Just try to do this. I will give you around 5 minutes. Okay. So this is the voltage across the capacitor. Okay. This is the voltage across the capacitor. And this is the current across the capacitor. This is the current across the capacitor. This is the voltage across the capacitor. And I think, so it is very much identical to this question, but here you have a voltage source. Okay, for if there is a voltage source, you can see the differential equation is there. Okay. The same way you can get the differential equation for that circuit. Please try to get it. So this differential equation, uh, it get when the voltage source is there. Okay. I think you can understand this differential equation, no? This differential equation you should be able to get. Okay. Uh, so try to get this one for this one. Okay, so try to get for this one differential equation quickly. The same theory you can use, okay? Hello, Kattad. ඔකට ගන්න පුළුවන් වුණාද ඒක? හරි මේක නම් ඉතින් අමාරු දෙයක් නෙමෙයි ඉතර. හරි. ඒතකොට ඇත්තටම මේක නම් ඔකට මම හිතන්නේ දන්නවා ඔගේ ඔය මේ කැපැසිටි එකේ වෝල්ටේජ් එක එන්නේ. හරි. ඔක ඩිස්චාර්ජින් වෙනකොට ඔකට ගන්න වෝල්ටේජ් එක එන්නේ V naught e to the power minus මෙන්න මේ equation එක. Okay, so you can directly apply this equation. Okay, so V naught is 10 volt e to the power minus t. You know the R, you can get the equivalent R here, and C is given. Okay, C is given. So VT, you need the 1 volt. Okay, VT should be 1 volt. Then you have to solve this equation and find the T. These are known. Okay, so you can put log E, and here also you can use log E. Okay, then you can find this T. Okay, so in this way you can find the time. Okay, so you can use this equation if you know this. Okay, but if you don't, you can get, actually I'm not expecting this answer. I am expecting the differential equation actually here. Okay, so how to get the differential equation? You know that the voltage across VT, the across capacitor is VT. Actually, you need to get the equation to find this VT, no? Okay, so if you directly write VT is equal to 1 over C, that is the current, ICT, let's say that ICT current, that is the current to the capacitor, ICT dt plus V naught is 10. Okay, what is the problem with this one? What is the problem with this one? You need to find the voltage, you need to find the differential equation to find the voltage, but here you can see the current term is there. Okay, but current term is not need here, because we are not asking, you are not asking to find the current, you are asking to find the voltage. Okay, so the current term should be eliminated. Okay, මේ current term එක අයින් කරන්න ඕන. එතකොට මේ equation එක valid හරි. This equation is valid. But you can't directly use it because the current term is there. You need to remove this current. So how to remove the current? Okay, so you can use actually the Kirchhoff law here. Sorry, Ohm's law. The IC is coming here, then the IC is coming to here. So I1 may be there. Okay, I1 minus IC will be there. Now this is the resistor and this is the resistor. You can get the equivalent resistor here. So equivalent resistor, through the equivalent resistor, all these IC is flowing. Okay, so if I find the equivalent resistor, if I say it R, right? මම දැන් මෙතන මේ equivalent resistor එක හොයන්න යන්න 1 1 8 12 plus 1 8 4. එහෙම නැත්නම් මේ 12 කියන එක වාට ලියන්න පුළුවන් 4 ඒවා 3ක් sorry 4 කියන එක ලියන්න පුළුවන් වාට 12 ඒවා 3ක් විදියට. එතකොට 12 ඒවා 4ක්. ඒ කියන්නේ මෙතන ඉන්නේ 3යි. හරි? මෙතන 3 වෙන්න ඕන ඉන්නේ. 3 ohms තමයි ඉන්නේ මෙයාගේ equivalent resistance එක. මම R කියලා ගන්නවා. හරි? එතකොට R කියලා ගත්තොත් R into ICT again equal to VC. So maybe you can find the IC here, then that is VCR. Okay, then you can, so now the IC term you have found, so you can substitute this value here. Okay, you can substitute this value here, then you can get the so only VT terms will be there, then you can get the differentiation. Okay, then you can find the VT. Okay, so maybe you so if I done this, okay, VT is equal to 1 over C integration. Now instead of IC, I will put VC into R plus VC into R dt. Actually, this VC is also, this is the VC, no? Okay, this is the voltage across the capacitor. Okay, so this is the voltage across the capacitor, VCT dt plus the initial voltage, that is 10 volt. I will put it as V naught. V naught is equal to 10 volt. Okay. So now you can see that only VC terms are there. Then what you need to do? You need to get the differential because you need to get rid of this integration. No? If the integration is there, it is very hard to solve this equation. So we need to make this equation as a differential equation. For that one, you have to do the integration both sides, this side and this side. You need not integration, the differentiation. You need to get the differential of both sides. So this one will be dVT dt equal. So the integration is there now. Integration, you get the differentiation. Though integration differentiation cancel, so you will have here VT into RC. Okay, and this V naught is a constant, that is a 10 volt. So it will become 0 plus 0. So this part is not there. So so this is the differential equation. There should be minus now. Okay. Okay. So actually this equation, when we write this equation, this IC is flowing through to the resistor. No, this IC is flowing to the capacitor. Okay. Right. Now අපි මේක මෙන්න මේ equation එක ලිව්වේ charge වෙන්නේ. So I use this equation. Okay. This equation. Right. So this IC is flowing to the capacitor. Flowing to the capacitor like this, in this way. Okay. So this is flowing to the capacitor. Flowing into the capacitor. Okay. Okay. But when, so it is charging. When it is discharging, this IC is flowing from the capacitor. Okay, this IC is flowing from the capacitor. So for the discharge in profit, when you are writing this, that means the IC is flowing from the capacitor. Okay. So this plus IC means it is flowing to the capacitor, but it is actually flowing from the capacitor. No? Okay. So this way it is plus. So now the current is flowing actually this side. So it is minus. No. So here this should be minus. Okay. So you have to put minus here. So this will be minus. Okay. So actual differential equation is dVt dt plus 1 over RC Vt equals 0. This is the differential equation. No. Okay. So you can see that in this, for this circuits, this E will be there. Okay, this E will be there. Okay, same way you can write. Okay, and I think it is easy to write the equation. So this is also correct, and you can write like this also. You know that current IC is equal to C dVt dt. This is the current IC. Okay. Okay. This is the current IC. Okay. And the voltage is Vt. Okay. So the voltage in this way. Okay. The voltage in this way, that is Vt. And if you apply the Kirchhoff law, okay, Kirchhoff law, you can directly write this as, okay. So it is like this, okay. ICR, this is the voltage across the capacitor, plus, not plus, it should be minus Vt, okay. Okay. So if you apply the Kirchhoff law here, okay, the voltage is in this way, no? Okay. Voltage is this way. So this is plus and this is minus. Okay, so it also plus, no? When you apply in the Kirchhoff law, this will be plus Vt. It is equal to 0. Okay. So instead of IC, you can put this C, this one. So it will be IC, that is this one. So RC dVt dt plus Vt is equal to 0. So you can see that it is the same equation. Okay. So this way also, using this equation also, you can get the equation, this equation, or maybe using the voltage equation also, you can get the equation. එතකොට මේක තමයි differential equation. හරි. ඔකට මේක නම් තිබ්බත් අරකට මම දෙන්න ඕන ලකුණු වලින් සෑහෙන්න දෙන්න. හරි. එතකොට මේක නම් ඇත්තටම solve කරන්න එච්චර අමාරු නෑ. මේක අර variable separation වලින් solve කර හැකියි. හරි. නිකම් මම කිව්වොත් එහෙම. හරි. මේ equation එක මෙතන හරි නේද? මෙතන මොනවා හරි ප්‍රශ්න තියෙනවද? Are you okay with this? This is I just apply the voltage, simply Ohm's law and Kirchhoff law. Okay? That is what I have done. So do you have any problem here? So you need to consider the voltage and current direction. That is very important, plus and minus, okay? So I think both way you can do, okay? In this question, okay? In this question, actually, this equation is used. This equation is used. And for this one, the Kirchhoff law is applied. When the Kirchhoff law is applied, E equal, this is the voltage source. That voltage source is equal to IR, that is the voltage of the capacitor, and this VC, that is the voltage of the resistor. Okay, VC. Then IR, the I can be written like this, C into dV dt. Okay, so by substituting that value, you can get this differential equation. Okay. Uh, you can substitute this to this one. Okay. If I give this question, if I give you the exactly this question, හරි මම exactly මේ question මෙන්න මේ වගේම network එකක් දෙනවා නම් ඔයාට කෙලින්ම පුළුවන් ප්‍රශ්නයක් නෑ search of flow දාන්න. හරි ප්‍රශ්නයක් නෑ. හැබැයි බැරි වෙලාවත් මම ඔය කට්ටියට මෙහෙම එකක් දුන්නොත් එහෙම මෙතෙන් ඉන්ඩක්ට් එකක් දැම්මොත් එහෙම මොකද වෙන්නේ? මෙතන ඉන්ඩක්ට් එකක් දාලා ඔක කරන්න කිව්වොත් එහෙම කොහොමද කරන්න වෙන්නේ? එතකොට කොහොමද කරන්න වෙන්නේ? එතකොට වාට ඔය මෙන්න මේ ඉක්වේෂන් වලින්ම යන්න වෙනවා. හරි? ඒකයි මම මෙන්න මේක කියන්නේ නැතුව අර ඩිෆරන්ෂියල් ඉක්වේෂන් එකෙන් යන්න කියලා කියන්නේ. මොකද මේ ගානම දීලා තිබ්බ ප්‍රශ්නයක් නෑ. මේක දාලා තිබ්බොත් ඔයාලට හදන්න පුළුවන්. හරි? ඇත්තටම මම මේ ඉක්වේෂන් වැඩි ක්ලාස් එකේදී highlight කරෙත් නෑ. මොකද මේවා solve කරලා ගන්න එක. මේවා මතක තියාගන්න ඕනේව නෙවෙයි. මේවා අපි solve කරලා ගන්න දේවල්. ඒ කියන්නේ solution එකක් මේක. හරි? ඒ solution අපි මතක තියාගන්න ඕනේ අපිට අදහසක් තිබ්බනම් ඇති. හරි? ඕක chat GPT වල ගහුවත් එනවා මේක. හරි? ඒකින්ද මම ඔය කට්ටියට හුඟක් වෙලාවට මේ ක්ලාස් එකේදී වුණත් මේ එන්කරේජ් කරන්න මේ ඩිෆරන්ෂියල් ඉක්වේෂන් එක ගන්න. හරි? එතකොට ඒක සෝල්ව් කරන්න ඩිෆරන්ෂියල් ඉක්වේෂන් එකත් ඔය chat GPT වලට දාලා දැන් සෝල්ව් කරන්න පුළුවන් ඈ. ඩිෆරන්ෂියල් ඉක්වේෂන් එක ෆොටෝ එකක් ගහලා chat GPT එකට දුන්නොත් ඌ සෝල්ව් කරලා දෙනවා. එතකොට ඩිෆරන්ෂියල් වෙන ටූලුත් තියෙනවා ඕන ඩිෆරන්ෂියල් ඉක්වේෂන් සෝල්ව් කරන්න. හරි? එතකොට ඒකත් එච්චර අමාරු දෙයක් නෙවෙයි. ඒකින්ද මම හුඟක් වෙලාවට මෙන්න මේකෙන් යන්නේ. දැන් බැරි වෙලාවත් මෙතන ඉන්ඩක්ට් එකක් තිබ්බොත් එහෙම ඔය කට්ටියට මේ ඉක්වේෂන් එක වැලිඩ් නැහැ. හරි? එතකොට ඔය කට්ටිය මේ ඉක්වේෂන් එක මතක තියාගෙන දැම්මොත් එහෙම වැඩේ යන්නේ. හරි. දැන් මේක හරි මෙන්න මේකට අයියේ මෙතන තියෙන RC ඒ කියන්නේ මෙතන රෙසිස්ටර් එකක් හරහා කැප් එක ඩිස්චාර්ජ් වෙනවා. ඒ වෙලාවට විතරයි මෙන්න මේ ඉක්වේෂන් එක වැලිඩ්. Okay. This equation is valid only for the capacitor is discharging across the resistor. But if there is an inductor or another component, this equation is no more valid. But if you know how to apply this Kirchhoff law and voltage law and how to write the equation, then you can easily write the equation. Okay. So now after that you can, if you need, you can solve the differential equation. Okay. If you need, you can solve the differential equation. And so solving differential. So actually, this is I think we can do in the say variable separation method, no? So here you have VT. Okay. Here you have dV dt. Okay. The RC is there equal minus VT. Okay. So you can get this one here and this one there. Okay. So you will have dVt 1 over Vt equal 1 over RC. This is dt, 1 over RC. So you can get this dt here. So this will be dt. Okay. Okay. So you can write this as 1 over Vt dVt is equal to 1 over RC dt minus. Okay. So you can get both side integration. So this is somewhat like 1 over x dx integration. This is ln x, no? Definitely it should be ln x. So that means ln Vt is equal to 1 over RC dt means t here. Okay. Then so you can write this. So you know that log 10 to the 100 is equal to 2. No? That means 10 to 2 is 100. Okay. So here actually the base is e. So that means e to this power, e to the minus 1 RCT is equal to VT, but the initial condition is there. Initial condition is there. V naught is there. So once you apply the initial condition, this should be V naught. Okay. So in this way, you can solve the differential equation. But this solution is not needed. Okay. This differential equation is enough. Okay. This differential equation is enough. Okay. Okay. So I think, do you have any question with this one? I think this is very easy one. මේක තේරුණා නේද? මම මේ ටක් ගාලා කරන්නේ වැඩි වෙලා නැති හින්දා. මම ලස්සනට ලියලා කරන්න බෑ. හරි? I don't have much time to do this clearly. Okay? So do you have any problem? Current direction එක පොඩ්ඩක් okay. Okay. So it is very simple thing. Okay. So you have done this when so the current direction and voltage direction, you know that. So that is very important when you are applying Kirchhoff law and Ohm's law. Okay. So you can see that this equation we write when the I is going to the capacitor. Okay. So I is equal to C dV dt and Vt is equal to I 1 over C up to some time IT dt like this. Okay. So this equation is when the current is going to the resistor, but now the resistor is discharging. That means the current is flowing from the capacitor. So this I will be minus, no? So this I will be minus. So this is not plus I, this will be minus. Okay. So that is it. I hope you got the answer, no? Is it okay? Yes, induct එකක් තිබ්බොත් ඕක ගන්න වෙනවා second order differential equation. ඉතින් induct එකක් තිබ්බොත් ඔය විදිහම තමයි කරන්න තියෙන්නේ. හරි? එච්චර අමාරු නෑ. So if the inductor is there, okay, if the inductor is there, like this, so you have the capacitor, okay, and a resistor, and let's say that there is an inductor like this, okay. So now the capacitor is discharging. This is plus, this is minus. Capacitor is discharging. That means current is flowing in this direction. Okay. Current is flowing in this direction. Okay. Capacitor is discharged. Okay. So this is the capacitor current ICT. And there is a current through the resistor IR. So IR is not changing. That is a constant current. And there is a capacitor flowing through the inductor. That is IL. Let's say that it is IL. Okay. So that is also changing with time. Okay. Now for the simplicity, I will forget this T. Okay. මම මේ T නැතුව ලියන්නම් equation එක. T දදා ලියන්න ගියපම වෙනස් මේ වෙලා යන හින්දා. හරි. but T තියෙනවා මේක මේ කියන්නේ IL එක T එක depend වෙනවා. මොකද මේක transient state එකනේ. At the transient state this IL is changing. This IC is also changing, but the current through the resistor is not changing. Okay. So, but simplicity, I will write IC, IL, and IR. Okay. So basically, one equation you can write as IC, IR plus IL. This is one equation. Okay. So that is Kirchhoff current law. Okay. Then you need to find the voltage across the capacitor. Okay. Voltage across the capacitor. Okay. Okay. So the voltage across the capacitor you need to find. That is, let's say that VT. I will tell it as VC. For simplicity, it is changing. Okay, VC. Okay. And now you can see that VC and VL, this one and this one are same, no? Okay. So here actually VC, okay, VC equal to VL. This is the inductor voltage. Okay. This is the inductor voltage. Inductor is charging that. Okay. Now the inductor is charging VC, VL. Then also and VC, this one also VC. Okay. This is VC. Okay. This the whole voltage is VC. Okay. Now you can write the equation. Okay. For example, you can write, maybe you can apply, so there may be many methods, okay? But what you need to do it, you need to apply the Kirchhoff law correctly. That is enough. Right? So if you apply the Kirchhoff law here, what happens? So there is no source. That means 0 is equal to, so the current is here, the current is flowing in this way. Okay, and the current is flowing this way. Okay. Okay, so you need to plus and minus. You need to consider plus and minus when you apply in the Kirchhoff voltage, right? Kirchhoff voltage law. Okay, so there is no source. It is 0. Okay, so this is the current IL that is through the inductor. So that is the voltage through the inductor. What is the voltage through the inductor? You know the equation that is for that one. So the voltage through the inductor is VL, that is equal to L di dt. No, this is the voltage across the inductor. Okay, so you can write it as L di dt. That is the voltage across the inductor. Now this one. So that is the voltage across the capacitor resistor, but the current is flowing in this way. So you are applying the Kirchhoff law in this way. Current එක මේ පැත්තට දානවා. Kirchhoff law එක apply කරන්න මේ පැත්තේ. එතකොට මේක minus වෙනවා. Minus IR R. So this is one equation. This is one equation. This is another equation. This is another equation. Okay. Okay, but we no need this I value. Okay. Now we are asked to find the voltage. No? Sometime you may be asked to find the current. Okay. If you are asked to find the current, you need to get rid of the voltage. බැරි වෙලාවට අර current හොයන්න කිව්වොත් එimhe මේ voltage ටික තමයි අයින් කරගන්න ඕන. හැබැයි දැන් මෙතන කියන්නේ voltage එක හොයන්න කියලා. එහෙනම් මම current වලින් වැඩන්නේ current අයින් කරගන්න ඕනේ. current අයින් කරලා පුළුවන් තරම් voltage value දාගන්න ඕන එතෙන්ට. හරි? Okay, I think we can do this. Okay, actually, this is the voltage across the inductor, no? Voltage across the inductor. That is equal to the capacitor across the inductor. Okay, so you no need to write this equation. You can directly write this as VC. Okay, so this is the voltage to the inductor, VC. Actually, this is VCT. Okay, this is VCT. මෙතනත් VC මනේ. එහෙනම් මේක මට ලියන්න පුළුවන් VC minus IRR, that is equal to 0. So it is so now VC should be there. No? VC should be there. In the differential equation, we need VC. So you can keep it here. Now, actually, we need to get rid of this IR. So how to find this IR? So IR is equal to what? IC minus IL, using this one. If this is A, using A, IR equal to IC minus IL. Now you can write this IC and IL with respect to voltages. No, in this way you can remove the current value. තේරුණා නේද? අන්න එහෙමයි ලියන්න ඕනේ. පොඩ්ඩක් මොලේ කල්පනා කරලා ලියන්න වෙනවා. Okay. So you can write IC, that is the current through the inductor. That is the current through the inductor. So you know that current through the inductor, IC, you can write as C dV dt, dVc dt. This equation, you know that, okay? So you can directly apply this one here. But you know that this is for charging, this is to charge in the capacitor, but here it is discharging. The current is flowing in this way. So this will be minus value, okay? So this will be minus value. So here, instead of IC, you can write it as minus C dVc dt. Now, write the equation for IL. IL ට ලියන්න බලන්න equation එක කට්ටිය. IL ට ලියන්න පුළුවන් නේද equation එක? IL කියන්නේ මොකක්ද? What is the IL? That is the current through the inductor. That is the current through the inductor. What is the value for the IL? Okay. That is the current through the inductor. Current through the inductor. Okay. This is actually those are given in the note also. Okay. Those are given in the note also. Okay. So you can see that this is the current. This is the equation I have written out. ඒක පේන්නේ නැතිම තමයි මේවට මම පෙන්වන්නේ. මේක තමයි කරන්ට් එක. ඉන්ඩක්ටර්. මේක හැබැයි ඉන්ඩක්ටර් එක ඇතුළට යන්නේ. අතනත් ඇතුළට යන්නේ ඉන්ඩක්ටර් එක. හරි? එතකොට ඒක ප්‍රශ්න තමයි ඈ. හරි මේක කරන්ට් එක. හරි? The voltage across the inductor is මේක. මේකෙන් voltage across the inductor මේක. Okay? So this is the voltage across the inductor. This is the current through the inductor. Okay? So now IL is the current through the inductor. So you can directly write that equation. හරි? වැඩි කල්පනා කර කර ඉන්න ඕන කෙලින්ම ලියන්න පුළුවන්. ලොකු දේවල් නෑ. මේ IL කියන්නේ මොකක්ද? What is this IL? That is the current through the inductor. This IL is the current through the inductor. මෙන්න මේ ඉන්ඩක්ටර් එක හරහා යන කරන්ට් එක. ඒතර කරන්ට් එකට වාට ලියන්න පුළුවන් කොහොමද? කරන්ට් එක ඉන්ඩක්ටර් එකේ කරන්ට් එක IL T on equal වෙනවා 1/L integration voltage across the inductor dt plus initial current. Okay, so now there is no initial condition, there is no initial current, so this I not, it is not mentioned, no? So you can assume that there is no initial current, so I not you can remove. Okay, so what is the inductor voltage? VL. That is actually VC, no? VC and VL is same. When you can circuit theory, VC is equal to VL. Okay. So instead of VL, you can directly write VC here. So you can write this IL as, okay, you can write this IL as 1 over L integration VC dt. This VC is a function of time, okay. I am not writing this T, VC dt. Now you can see that. Now this is the IR, no? So now you can substitute this value to here. So what is the equation you get? VC is VC minus, instead of IR, okay, this is the IR, okay, instead of IR you can apply this one. So it is multiplied by R again. So minus, so here it is minus, no, this minus and this minus, it will be plus. This minus and this minus, it will be plus RC dVC dt, okay. And here also minus minus, it will be plus, okay. This minus and this minus, it will be plus 1 over L, R 1 over L, that means R over L integration VC dt, okay. So that is equal to 0. That is equal to 0. So let's say that if you have a charge here, source here, what happens? If you have a source, then you need to consider the source also. Okay, you need to consider the source also. But if the source is there, this may be not discharging. Okay, it may be a charging circle. Okay, if it is a source there, so maybe this is not 0. You can have a value here, maybe like E. Okay, okay. So if the source also there, it is not much difficult. Okay, the same way. Okay, but here no, it is not source, so you can write like this. Now to make this a differential equation, what we need to do? There is an integration. We need to cancel the integration. For that one, we need to get the differential of all the terms. Okay, so this will be dVC dt plus RC. So this is one time it is a first derivative. So once you do the derivation with respect to t, we will have the second derivative, no? That is d square v d square v dt square plus r over L. Once you get the derivative of this integration, only Vc is there. So now you can write this as Rc d square Vc dt square plus dVc dt plus RL Vc equal 0. Now you need to find this Vc. Okay, you need to find this Vc. So by solving this differential equation, you can find the Vc. Okay, no need to solve. Okay, no need to solve. If possible, you can solve. Okay, so how? So can you tell me how to solve this one? What is the technique? Maybe you can use. Just tell me. I think separation variable may be not okay for this one. So what is that is the standard method? No, what is the standard method? I can't remember that name. Can anyone remember? That is the standard method of solving the differential equation. There is a name. Any differential equation you can solve using that one. No need the yes, integrating factor. Yeah. So that is the way of solving this one. Okay. So if possible, so if you get this, you have 8 marks. But if you solve this, you get 2 marks. Okay. So if you have time, you can do the you can find the solution. Okay. If not, just skip finding the solution. Okay. So that is why I asked you not to remember this equation. Okay, this equation is not valid at all the time. This is valid at a specific time when the capacitor is charging, discharging across the resistor. But it is not happening every time. හරි ඒක කොයි වෙලෙත් වෙන්නේ නැහැ. Right? So maybe rather than keeping remember this kind of equation, it is better if you practice how to get the differential equation and if need to solve it. Okay, that is the better way. Okay, I think that is okay. We'll go to the next one. Okay. So you can see that this is a steady state. So what happened? So that is very simple. You asked to, actually this is not, you will get around 10 to 15 marks here. Around this one, you get around 35 marks. You are asking to find the capacitor energy, stored energy also. Okay, so you know that it is also given in the note. Okay, so the capacitor energy of the capacitor, you can write it as integration of Vt it in the time domain. This is the energy. Okay, so voltage into current, you need to integrate it within the time period. So you can find the energy stored in this capacitor. The C is also there. C is also there within a time period, within some time period. And this can be simplified as, you can solve this as half C V square. Okay, Wt is half C V square. So V, you know what is the V. Okay, you know what is, if you know the V, C, then you can find the power through the capacitor. Power dissipated from the capacitor. Energy dissipated, energy stored in the capacitor. Okay, in this way. Okay, so you can use either this equation or this equation, then find the energy. Okay. Okay. Now we will move to this one. So you can see that. So you can see that now. Now very important thing is there. What happened here? Now this means that the switch is on when t is equal to 0. T එක බිඳුව වුණාට පස්සේ තමයි ස්විච් එක on කරන්නේ. ඒක නම් එහෙනම් එතකල් ස්විච් එක වහලා තියෙන්නේ. එහෙනම් මෙතන තියෙන්නේ t equal -0 කියලා. ඒ කියන්නේ 0 වලට පස්සේ 0 minus එකක් මේ දාලා තියෙන්නේ. ඒ කියන්නේ මෙයා අරින්න කලින්. ඒ කියන්නේ මේක වහලා තියෙනකොට. Okay? So that means when the switch is closed, you need to do this question when the switch is closed. Okay? So when the switch is closed. Okay? So now the switch is closed. Okay? Switch is closed. Okay? So the switch is on at t equal minus, when the t is equal to 0, switch is on. Now switch is off. Okay? So at that time, it is said that this is in steady state. That means this capacitor is open circuit. So there is no capacitor. Okay? So there is no branch. The current coming through the battery. Okay? Going through this resistor and this resistor. Okay? So you are asked to find the current to this resistor. Okay, this side. ඒක තනියම හදන්න මම හදන්න ඕනේ නැහැ නේ ඒකනේ. I think that is very easy one. Okay. You can do it by yourself. No? Maybe you can, so maybe you can apply Kirchhoff law here. Kirchhoff law here. Okay. And again, you can apply the Kirchhoff law here. Maybe for this one. Okay. So then I think you can find this. Okay. For example, this is this current. Let's say that this current is I, and this current is simple line. So this current will be I minus simple I. So if you apply the Kirchhoff law, then 18 volt is equal to I into 12 plus I minus I into 6. This is the this is when I apply the Kirchhoff law in this loop. Okay. If I apply the Kirchhoff law in this loop, again 80 is equal to 12I plus 12 simple I. Okay. I think you can, so there are two unknown parameter, capital I and simple I, and there are two equation. So you can solve this equation and find I. Okay. So you can do that by yourself. So this kind of question also will be there and you will get around 10 marks. Okay. 15 marks, around 15 marks. So I think for this question, I hope you can get, this is not a 25 marks. In your paper, this will be a 50 marks question. Okay. This will be a 50 marks question. So you can do around, you can get, I think around 45, more than 45, I hope you can get. Okay. Okay. So again, I ask you to do this question 2 part B. Okay. No need to find this damping. Okay. So try to do this one. I will use. Yeah. So try to get this equation. Try to get this equation. Try to get that equation. I will give you around 5 minutes. Hello. Gathering. Okay. සර්කිට් එක මිනිමයිස් සර්කිට් එක මිනිමයිස් කියන්නේ අර මේක හොයලාද මේ ඉන්ටර්නල් සොරි සමග ප්‍රතිරෝධය හොයලාද සමග ප්‍රතිරෝධය හෙව්වත් ඒක මේ එකපාර අයි හොයන්න හම්බෙන්නේ නැහැ කට්ටියට. අයි දැන් මේකේ මෙයාගේ සමග ප්‍රතිරෝධය කියන්නේ මේ අයි හොයා ගන්න පුළුවන්. ඒ කියන්නේ 12 6 සමග ප්‍රතිරෝධය කියන්නේ 12 2 12 ගුණ 4ක්නේ. මෙතන ඉන්නේ සමග ප්‍රතිරෝධය 4යි. එතකොට 4 පස් 4 ප්ලස් 12 කියන්නේ 16යි. එතකොට 16 බෙදීම 18 තමයි මේ මෙතනින් එන කරන්ට් එක I. හරි? හරි? අ, එතකොට 18 බෙදීම 16 කියන වැලියු එක තමයි එන්නේ එතන කරන්ට් එකට. හ්ම්. එතකොට මේ මුළු කරන්ට් එක මෙතනින් එන මුළු කරන්ට් එක I. ඒක අපිට හොයන්න පුළුවන් 18 බෙදීම 16 කියලා. V සමාන IR දාපුවම. හරි? මේ V සමග ප්‍රතිරෝධය ගත්තේ මම මෙතන. මෙතන මේ දෙකේ සමග ප්‍රතිරෝධය එනවා 4ක්. 4යි 12යි 16යි. හරි? එතන මේ මුළු රෙසිස්ටර් එක 16යි V සමාන IR. I 16 සමාන 18. එතකොට I එනවා 18 බෙදීම 16ක්. Okay. So that is the total current. Okay. But now part of current is flowing through this one and part of current coming to this one. Okay. So you need to find this simple line. So you can find this total I here. Okay. Then by applying this total I value to this one or this one, it is better to apply this one. You can find the simple line. Okay. I think directly you can't find the simple line. Directly මං හිතන්නේ හොයන්න බෑ ඔය කට්ටියට simple line බලන්න පුළුවන්ද කියලා පුළුවන් වෙන්නත් පුළුවන්. මගේ ඔළුවට එන්නේ නැහැ ඒක. simple line directly හොයන්න පුළුවන් විදිහක්. හරි. පුළුවන් නම් පුළුවන් නේ. මං හදන විදිහම නෙමෙයි සමහරට මේ ඔය කට්ටියට වෙන මීට වඩා ලේසි විදි තියෙන්න පුළුවන් නේ. මේ මම නිකන් ඒ වෙලාවට හිතලා ලියන ඉක්වේෂන්. ඒතර ඔය කට්ටියට හරි මේ හරිද ඔයාගේ උත්තරේට හරිද? හරිනේ මම ඔකට ඒ ප්‍රශ්න මොකුත් මග ඇරියේ නෑ නේද? මොන හරි මග ඇරිච්ච ප්‍රශ්න තියෙනවා නම් මට ආපහු දාන්න. ඒක ඕකේ නේ. හරි. හරි දැන් මේක RLC circuit එකක්. Okay, this is RLC circuit. So so definitely it should be a this kind of this is a second order differential equation. Definitely it will be a second order different. At least try to write the equation. Maybe if you write the equation correctly, some part is there. Okay, so you will get some marks. හරි equation ටික හරියට identify කරගෙන හැබැයි when you identify the so you need to identify the status of the circuit. Okay, sometime the circuit may be discharging or charging. That status you need to identify. That is very important. Okay, we will do this one. Okay. Now you need to get the differential equation to find this V1. Okay. So the V1 should be there. V1 should be there. Then you can have this value. Okay, this value should be only V1 should be there. Only V1 should be there. There is a V2 also. V2 also there. Okay, V2 also there. Now, how to find the differential equation? So this is differential equation means this is should be the for the transient state. Okay, is it status here? Sorry. Okay, actually this is for the transient state, okay, but it is not described, it is not mentioned here, but it is for the transient state, okay? Okay, okay, for the transient state, what happened? If it is steady state, what means? That means this capacitor will be vanished. මේ capacitor එක නැති වෙනවා. මෙතන මේ inductor එක නිකම්ම short circuit වෙනවා. එතකොට එන්නේ මෙන්න මේ resistor එකයි මේ resistor එකයි විතරයි. එතකොට ඉතින් මොකක් හරි කරන්ට් එකක් හොයන්න කිව්වොත් එහෙම ටක් ගාලා හොයන්න පුළුවන් ඈ ස්ටඩි ස්ටේට් වැඩක් නැහැ එතකොට. එතකොට මේක ට්‍රාන්සියන්ට් ස්ටේට් එකේ තමයි මේ අහලා තියෙන්නේ. ට්‍රාන්සියන්ට් ස්ටේට් එකේදී තමයි අපිට ඩිෆරන්ෂියල් ඉක්වේෂන් එන්නේ. හරි? හරි. දැන් ඔකට මේකට ඉක්වේෂන් දැන් මෙහෙමයි මම ලියන්නම් අපි ලියාගෙන යන් ඉක්වේෂන් ටිකක් හරි. එකපාරටම අපිට හිතන්න අමාරුයි. දැන් අපිට මෙතන V1 ගන්න ඕනනේ. We need to get the V1 here. Okay? So you can see that V1 minus V2. What is this? This is the voltage across the resistor. What is V2? V2. What is V2? Someone tell me what is V2 and what is V1? So you can directly see what is V1 and what is V2. This is 0, okay? This is grounded, no? So this is 0. So V1 minus V2, that is the voltage across the resistor. And what is this V2 and what is this V1? So that identification is important. මොකද්ද මේ V2 කියන්නේ V1 කියන්නේ? V2 කියන්නේ මොකක්ද voltage එකක්ද? V1 කියන්නේ මොකක් කරා voltage එකක්ද? අක්කලකින් V2 is across which component? V1 is across which component? Yes, V2 inductor, very good. And what is V1? V2, this is V2 is the voltage across the inductor. What is V1? Yes, very good. Okay, so that you need to identify that one. Otherwise, you can't do this question. Okay, actually, V1 means the voltage here. V1, this voltage is 0. Okay, so V1 minus 0 means the voltage difference between these two terminals. This two terminal means these two terminals. Huh? Okay, so that means that is the voltage across the capacitor. So V1 is the voltage across the capacitor. So I think now you can write some equation. Okay. Now you can write some equation. Okay. And you can see that the current will be flowing here. Okay. And one current is flowing through this branch. Let's say that I1. And another current is flowing through this branch. Let's say that it is let's say it is IC because that is the current flowing through the capacitor. This is the current flowing through the resistor and inductor. Okay, so I will write it as IRL or something. So that is the current flowing through the resistor and inductor. Okay. So you know that this I is equal to IRL plus IC. Okay, tell me, this are these constant? These current are constant? No, these current are not constant. Okay, all these current are time of function. It is varying with respect to time. Okay, okay. You know that I is equal to IRL, current to the resistor inductor. I will write it as IL or something. Okay, for easy. Okay, that is also correct, no? So that is going through the inductor. Okay, this current is going through the inductor. So I will write it as IL and IC. IC means the current through the capacitor. Okay, and these are not constant. No, these are function of time. This IT is changing. IL is also changing. IC is also changing. Okay. So these are function of time. මම මේ t අකුර ලියන්නේ. හරි. මම මේ t අකුර ලියන්නේ නැතුව තමයි equation එක ලියන්නේ. Okay. Um, I, I, I don't think you get the confusion. Okay. So these are function of time. Okay. These are function of time. These are varying with respect to time, but I am not indicating that one. Okay. But keep remember, these are function of time. Right? Okay. Uh, okay. So that is one equation. I is equal to IL plus IC. Okay. But we need to see the V1, okay, voltage. Okay. So directly you can write uh, the so there is directly you can write the uh, relationship between IC and V1. What is that one? What is the relationship between IC and V1? That is the voltage across the capacitor, no? Okay. So the voltage across the capacitor, you know, okay, V1 is equal to V1 is also changing. Okay, V1 is also a function of time, V1t. This V2 also changing, it is V2t. Okay, now we are not writing this t. Okay, we are only writing V1. Okay, V1 is equal to 1 over C integration. C means 1 over 4. Okay, okay, 1 over C integration. This is V1. What is IC dt? Okay, so this is one equation. Okay, but this IC we need to get rid of. Definitely we need to get rid of this IC. Okay. And V2 is also a voltage across the inductor. So you can write V2 as L into DIL dt. දැන් මේ equation ඔය කට්ටිය මතක් වෙන්න ඕන. දැන් මේ equation මම ලියවා කියලා බය වෙන්න එපා. මොනවද මේ කියලා නෙවෙයි. මෙයා මේ කොහෙන් ආපු ඒවද කියලා හිතන්න එපා. මේ මම ලියන්නේ ඉන්ඩක්ටර් එකේ voltage එක. මේ මම ලියුවේ capacitor එකේ voltage එක. V1 කියන්නේ capacitor හරහා voltage එක. V1 is the voltage across the capacitor. V2 is across the inductor. Okay. So these equations are given. Okay. So you need to familiar with this equation. That is very important. So V1 is equal to 1 over C IC dt. V2 is equal to L DIL dt. Okay. Uh, okay. Now I think you need to, yeah. So another equation also you need to get. Okay. So it is better if you get, okay, the V1 should be there. No? Actually, we need to get rid of this I terms. Okay. So you can write this equation. Okay. දැන් මෙහෙම මේක එකපාර ඔලුවට ආවේ නැහැ කියලා ප්‍රශ්නයක් නැහැ. හරි. මේ ඔකට මේ ඉක්වේෂන් ලියාගෙන යන්න. හරි. ඉක්වේෂන් ලියාගෙන යන්න මේ ඉක්වේෂන් වලට ලකුණු හම්බ වෙනවා. Okay. If you have written this equation correctly, you will get marks. Okay. You will get most of marks. Okay. Actually, that is the analysis. No? Okay. So our subject is applied circuit analysis. Right? So that is the subject. Right? ඔකට්ටියගේ ඔකට්ටිය පොඩි කාලේ නම් මේ equation විසඳලා තියෙනවා, simultaneous equation විසඳලා තියෙනවා. 11 වසරට එනකල් සුළු කරලා තියෙනවා. කැල්කියුලේටර් උත් නැතුව නේ 12 වසරට එනකල් මනේ කැම්පස් එනකල්ම කැල්කියුලේටර් උත් නැතුව සුළු කරලා තියෙනවා. ඊට පස්සේ අවකලනේ අනුකලනේ හදලා තියෙනවා. හරි. ඒව වැඩක් නැහැනේ අපිට. හරි. ඔයා මෙන්න මේ ඉක්වේෂන් ටික හරියට ලියා ගන්න එක තමයි වැදගත්. ඒක තමයි සර්කිට් එකට අදාළ. හරි. එතකොට ඒකට තමයි වැඩි හරියක් ලකුණු තියෙන්නේ. හරි. So this writing the equation is very important. Actually, that is applied circuit. Okay. Others are related with mathematics. So this is not the maths module. This is applied circuit analysis. Okay. So I am not focusing on maths. Okay. මටත් වැඩි maths බෑ ඇත්තට. So that is why I am not focusing on that one much. Okay. Okay. So I think we can write like this. Okay. If we write the VG, I'm putting the Kirchhoff maybe in this loop. Okay. I'm putting the Kirchhoff in this loop. So VG is equal to IR, I into 4, that means 4I. This is 4I. And that is the V1. Okay. V1. So that is the voltage across the capacitor. So I can directly write it as V1. Okay. So VG is equal to IV1. So VG is given. So you can use this VG. And now, so actually, now you can write instead of this equation, I can write the current across the capacitor. No. So the current across the capacitor is IC is what? IC is C into dV1 dt. This is the V1 is the voltage across the capacitor. So IC is the current across the capacitor. So this equation is okay. And the current across the inductor IL, that is equal to 1 over L integration of V2 dt. No. So if I apply, so you know that I is equal to IC plus IL. Okay. So VG is equal to 4 IC plus IL plus V1. Okay, V1. Okay, so you know that. So using this one, okay, using this equation, okay, using this equation and this equation, I is equal to IL plus IC, I can write like this, no? VG is equal to 4 IC plus IL plus V1. Okay. Then, so I need to get rid of this IC and IL. No? Keep it that in your mind. හරි අපි මේ current එක තමයි අයින් කරන්න ඕනේ. හැබැයි ඔකට current වලට ලියන්න කිව්වොත් voltage ටික අයින් කරන්න ඕනේ. හරි? If you ask to find the current, you need to get rid of the voltage. But in this case, you are asked to find the voltage V1. So you need to get rid of the current. Okay. So VG is equal to 4 IC. IC is C dV1 dt. IL, that is 1 over L integration V2 dt plus V1. Okay. Now I think we get, no? Okay. So, okay. So what you need to do? You need to get rid of this integration. For that one, you need to get the derivatives. Okay. So you need to get the derivative here, dVg dt. You need to get the derivative here. So it will be 4C. So you are getting so this is first derivative. If you are getting another derivation, so it will become a second derivative. That is d square v1 dt square plus, so here 1 over L, and this integration will be cancelled. So you will have V2 here plus this V1 is also, it is not a constant. Okay, this V1 is the voltage across the capacitor. So it is a function of a time. So it will be d1 dt. Okay. So I think this is the equation. Okay. V2, I think V2 terms are there, no? V2 term is not here, no? The V2 term is not here. So you need to get rid of this V2 also. Okay. Now you get this equation. Okay. This equation. Okay, you get this equation. No, I see not minus. Why? Because the IC is going through the capacitor, no? So ඒක ඔයා mark කරන පැත්තට තමයි. Okay, so it is just like you mark. So this is the plus side of the source. So current is flowing in this direction. So it is I. So one I is going through this branch. Another part of I going through this part. So this capacitor, that part is through the capacitor. So we can define it as a capacitor current. So it will be plus, no? It is going through the capacitor, not going out of the capacitor. If it is going out of the capacitor, it will be minus. Okay. So now it is going into the capacitor. Okay. So in this equation, it is plus. And the inductor current is also going to the inductor. So in this equation, it should be plus. Okay, it not be minus. But when you apply Kirchhoff law, sometime it can be, for example, if you apply the Kirchhoff law in this direction, this IC will be minus value. හරි. දැන් මේ equation වල IC කියන එක plus වෙන්නේ. හැබැයි Kirchhoff law දානකොට ඔයා දාන පැත්තත් එක්ක සමහරලාට ඒක minus වෙන්නත් පුළුවන් plus වෙන්නත් පුළුවන්. Okay? Is it okay? So in this case, the current is flowing through the capacitor and inductor. So definitely these are plus. It is going through the capacitor. So when you are writing the transient equation for the capacitor and inductor, you have to use the plus value. Okay. But when you are applying the Kirchhoff law based on the direction, sometime it can be minus. Is it okay? In previous state, it is taken as minus because it is discharging. So that is why I take it as minus. Okay. If it is discharging, you have to write this equation. When you are writing this equation, you have to write it as minus. Because this is the current to the inductor, current through the inductor, not current going out from the inductor or capacitor. Okay. But sometime මට දැන් මතක නැහැ ඔයා දැන් මම දැන් මොකක් හරි කර්චොෆ් එකක් දානකොට සමහරට මයිනස් දැම්මද දන්නේ නැහැ හැබැයි. Okay. ඒ දාන්නේ ඩිරෙක්ෂන් එක බලලා හරි. එතකොට ඔයා කර්චොෆ් දාන ඩිරෙක්ෂන් එක තමයි ප්ලස් මයිනස් වෙන්නේ. Okay. Okay. So if the source is there and if you are asking it is transient, definitely it is charging, no. If the source is not there, it is the discharging, no. Okay. For example, in this case, okay, the source is there connected, so it is charging. Okay, but here it is not, there is no source. Okay. So that means it is discharging. So that is how you have to find charging or discharging. Okay. Sometime it may be questionable. At that time you can assume. Okay. සමහර වෙලාවට ඒක questionable වුණොත් ඔය කට්ටියට ඒක assume කරන්න පුළුවන්. If the charging or discharging is questionable, okay, if it is not clear, just assume it. Write it, you assume this as charging. Then I will write the equation according to that one. Right? Okay, did you get it? So when I mark it, I am considering your assumption. If you assume that this is discharging, so I also assume that it is discharging and I see the marks according to that way. Okay. So if it is in this way, it is very clear. Charging and discharging you can identify clearly, but if it is not clearly identified, you can make an assumption. Okay. Okay. Now, if I go to this one, so you need to get rid of this V2 also. Okay. The V2 also you need to remove this V2. One V2 is there. No? So how to remove the V2? You can write another equation. You know that V1 is equal to I inductor IL ILR and V2. ILR plus V2. This is okay, no? So you can write this V2 as V1 minus ILR. This equation, I think you clear, no? Okay. I just apply the Ohm's law to this branch. Okay. And here also we write this, no? V1 minus V2 is equal to IRL. You can write, okay. If you apply the Ohm's law between this one, V1 minus V2 is equal to ILR. This is the IL is the current through the resistor and inductor. So that is ILR. Okay. Then V2 is V1 minus ILR. Okay. So that is clear. Okay. V1 minus ILR. ඇත්තට මේවා නිකන් හදන්න ඕනේ නැහැ හරි. ඔය කට්ටිය ඒ කියන්නේ ඔය කට්ටිය මේක ඉක්වේෂන් එක මට ලොකු ප්‍රශ්නයක් නැහැ. ඔය කට්ටිය අන්තිම මේකට ගත්තේ නැත්තම්. ගත්තේ නැහැ කියලා. හරි. දැන් මේවා නම් එච්චර අමාරු නෑ ගන්න පුළුවන්. හරි ටිකක් ලොකු සර්කිට් දීලා ගන්න බැරි වුණා ප්‍රශ්නයක් නෑ හරි. So this is V1 minus I2R, okay, ILR. So IL again you know, IL is V2 is equal to V1 minus IL is again V2 is there, no? I think this question is somewhat difficult. This way you can do okay. You know that V2 is equal to V1 minus IL. IL is the current through the inductor, no? So R is there. IL is the current through the inductor. So the current through the inductor you can write as again integration of VL. So that is V2, no? V2 dt in this way. Okay. So integration is there. So to get rid of this integration, you need to get the derivative. So you will have dv2 dt equal to dv1 dt minus rv2. So here it has a two variable. No? It has a two variable, and solving this differential equation is difficult again. Okay. Mm, so can you suggest a way to get remove this v2? Definitely you need to remove this v2. Okay. Are there any direct way to remove this v2? Okay, now I think no, it is not come to my mind. Okay. Uh, anyway, maybe you can go for a uh, final answer. Okay. So in this derivation, okay, I will now I is not I don't have time to uh, spend much time. Okay, here. Okay. Anyway, only you will have the V1 and VG. So you need to get rid of this V2. Okay. To get rid of this V2, there is a method actually. We found the method. Okay. You can get the another differential equation, and you can find this V2 value with respect to V1. Okay. With respect to V1, but I don't know how to solve this one. Okay. This kind of differential equation I can't remember how. Are there a way to solve this differential equation? This V1 is also variable, V2 is also variable. So are there any way to solve this differential equation? කවුරු හරි දන්නවද මේ වගේ differential equation එකක් සුළු කරන්න පුළුවන්ද? Someone know? කොහොමද මට යාගේ නම් මතක නැහැ. පුළුවන්ද මේ වගේ differential equation එකක් solve කරන්න? මට නම් මතක නැහැ ඇත්තටම. දැන් මෙතන variable දෙකක් තියෙනවානේ v2 ත් variable එකක් v1 ත් variable එකක්. අපිට v2 හොයාගන්න ඕන v1 වලින්. මේ differential equation එක විතරක් මදි නේද? එහෙම බෑ මං හිතන්නේ. ඒක දර්ශන සර්ගෙන් තමයි අහන්න වෙන්නේ. Okay, we have to ask it from Darshan sir. Okay. Maybe if you have time, you can check. Okay, you can check with him how to solve this kind of differential equation, or maybe there may be another way. Okay, I don't see a way now. Okay, if you write the equations for the V2, definitely there will be some differential equation again. But you can get two differential equation. Okay, you can get another differential equation definitely if you apply the Kirchhoff law and through another, for example, in this root, in this loop, you will get another differential equation. Okay, you will get another differential equation with V1 and V2. Again, you have two variable. So there will be two differential equation with two variable. Maybe using that, you can find V2 with V1. I don't know. Okay. So, so anyway, if this question is there, actually I am not. So if you couldn't get this expression, okay, your mark will not be reduced. Okay, your mark will not be reduced. Maybe 1 or 2 marks will be reduced. but other marks you will get, okay? To for the for writing the correct equation, okay? Okay, is it okay? Okay ද? ඔකට වෙන මොකක් හරි තියෙනවා නම් කියන්න. දැන් මේක මට අරක මේ V2 අයින් කරන්න හැටි තේරෙන්නේ නැහැ මෙතන නේ. අපි ආපේකේ V2 ගත්තනේ මම හිතුවේ මෙතන V2 තියෙනවා කියලා. උනාට V2 නැහැ ඒකේ. හරි. V2 නැතුව ගන්න ගියම අමාරු වෙනවා. මොකද මෙතන V2 ට ඩිෆරන්ෂියල් ඉක්වේෂන් එකක්ම තමයි එන්නේ. හැබැයි ඒක V2 ගෙන් විතරක් ගන්නත් බෑ අපිට. හරි. V2 විතරක් වෙන විදිහට ඩිෆරන්ෂියල් ඉක්වේෂන් එකක් ගන්නත් බෑ. හරි. ඒතකොට ඩිෆරන්ෂියල් ඉක්වේෂන් දෙක තුනක් ගත්ත හැකි අපිට. සර්ච් ඔෆ් ෆ්ලෝ එක මේ වෝල්ටේජ් ෆ්ලෝ එක ලූප් වලට දාලා. ඒකට ඒවා සෝල්ව් කරලා තමයි මේ V2 V1 අතර සම්බන්ධයක් හොයාගෙන ඒක මෙතෙන්ට ආදේශ කරන්න වෙන්නේ. හරි. ඕකේ. ඕකේ. ඒක තේරුණා නේ සාමාන්‍යව කට්ටියට? Do you have any problem with that? Okay. I don't worry, because if we type this differential equation maybe actually in MATLAB also, you can get the solution from MATLAB also. Okay. So it is not much problem. Okay. But writing the equation is very important. Okay. Okay. So and here it is asking that the damping status of the circuit. Okay, but this is not we haven't done this part. Actually, you maybe know that there are three types of damping status. Okay, it is not we haven't much time to complete it with the one credit module. Okay, so that is why I skip that part. Okay. So there are I will just tell it is not come to the exam. Okay. So there are three type of damping maybe. You have heard overdamp, overdamp. Here the damping ratio is greater than 1 normally. The damping ratio is considered greater than 1 and it is say that there is no oscillation. Oscillation and response is slow here. Okay. And there is another one critical damp. Okay. So that is the damping ratio is equal to 1. Here also no oscillation, but it is a fast response, okay? It has a fast response. And there is underdamp. So that is tau is equal to, tau is less than 1. So the oscillation happen. And it is decaying. So that means the signal is decaying like this, oscillating and decaying like this. The amplitude is decaying, okay? So these are the three damping status. And for the 2 credit and 3 credit, the 3 credit module, the damping ratio also there. Okay, you need to find the damping ratio and you need to verify it is overdamp, critical damp, underdamp. But for the your module, 1 credit module, it is not relevant. Okay, so you need to find this. You no need to worry about this damping status. Okay. Okay, so this is a sinusoidal excitation. So we no need to focus on that one. Okay, because these are sinusoidal one. Okay. Okay. And if maybe let's say that okay, if you consider this one, let's say that you turn on the switch, so it is in steady state. Okay, so at t equal to 0, this is turned on. This switch is turned on. Okay, so once it's turned on, then can you find the current through the I? Okay, so that means it is at the discharging. Okay, it is at the discharging. Okay, So can you try to find that one? It is very easy, okay? It is just like this equation, this question, okay? So if I ask you to find the current through the 12 volt 12 ohm resistor I, when the switch is on, when the switch is off at the transient state. So can you find it? තේරුණානේ මේ ස්විච් එක දැන් වහලා තියෙනකොට එයා ස්ටඩි ස්ටේට් නේ. දැන් මේක T සමානයි බිඳුවේදී අරිනවා. හරි. එතකොට මොකද වෙන්නේ? මෙන්න මේ රෙසිස්ටර් එක තමයි ඩිස්චාර්ජ් වෙන්න පටන් ගන්නේ. හරි. එතකොට ඒක ඩිස්චාර්ජින් එක. හරි. අන්න ඒ වෙලාවේදී මෙන්න මේ කරන්ට් එක හොයන්න පුළුවන්. ස්ටඩි ස්ටේට් එක නෙමෙයි. අන්න ඒ වෙලාවේදී මේ කරන්ට් එක හොයන්න. මම ඔකට විනාඩි 15ක් විතර විනාඩි 10ක් විතර දෙන්නම් චුට්ටක් බලන්න ඒක හදන්න. මම ඊට පස්සේ විනාඩි 10කින් විතර එන්නම් අර S ඩොමේන් ගානක් හදමු. ඒක පොඩ්ඩක් හුරු වෙන්න. හරි. චුට්ටක් බලන්නකො. So try to do that one. Okay. So when the switch is on, that means so your question may be like this, okay? Okay. Your question is like this. Find simple I at t is greater than 0 if the circuit is in transient state. If it is a steady state, what is the current? Steady state means this capacitor is fully charged, fully discharged. That means no current. The simple I is 0 at the steady state. Okay. So when the t is much time greater than 0, so maybe the capacitor will be fully discharged. So there may be no current. The I is equal to 0. Okay. So find I at this time. If the circuit is in transient state, just take around 10 minutes. I will come after 10 minutes and we will do one question related with this parameter. Okay. So I think now you are familiar with how to apply this equation. Okay. So please do this. You can refer the equation in your notes. Okay. Okay, have you done? Should I do this? I just write the equation only. Okay, no need to solve. Okay. Okay, so that means so when this switch is off, it is a steady state. That means this capacitor is fully charged. Okay. So once you on this switch at t is equal to 0, that means this capacitor is starting to discharge. That means if it is plus, you can see that. Okay, you can assume that. Okay, but in a practical way also you can assume it. Okay, so you know that this battery, the current is flowing in this direction like this. No, okay, so definitely this the capacitor, this one will be plus, this side will be minus. Okay, definitely. Okay. So when this switch is on, okay, so that means this capacitor is starting to discharge. So that means the capacitor current is flowing through this direction. Okay, and one current is flowing, one portion is going through this one, that is simple I. Okay, one portion is going through this one, so that is IC minus I. Okay, now you can see that this IC also changing, okay, with respect to time, but I am not writing this T. I am writing this as IC. Okay. Now this part is not there. No? Now this part is not there. Only this circuit is there because this is on. Okay. Now you have to find this I. You have to write the equation to find I. Okay. So definitely you will get a differential equation. Okay. So how to write the equation? How to write the equation? Okay. So for example, maybe you have to apply the Kirchhoff law. Okay. Definitely. Okay. So now you need to find the I. Okay. Now you need to find the I, not the voltage. Not the voltage. Okay. So voltage value you need to get rid of. You need to you need to you need to you need to see only I. Okay. I should be there. Okay. Um, okay. So for simplicity, I will assume this as VC. Okay. The the voltage across the capacitor is VC. Okay. So voltage in this direction. Okay. In this direction. Okay. Voltage is in this direction. Okay. Because this is plus and this is minus. Okay. So you need to mark the direction. Okay. When you apply the Kirchhoff law, the direction is there. So everything you need to mark the direction. Okay. Okay. Now if you apply the Kirchhoff law, okay, if we apply the Kirchhoff law to this terminal, I am applying it in this direction. Okay. So now the voltage across the capacitor is ICR. Okay, so it is in this direction. Okay, so that voltage in this direction. So that is IC2 plus now I am in this direction. I am going in this direction. Okay, now uh, across 6, it is IC minus I into 6. Okay, so IC minus I into 6. This is the voltage across this resistor. So this is also in this side. I am going in this way. No? So this is also plus. Okay. Now this is the voltage. Now voltage across the capacitor. Is it plus or minus when I am going from this direction? Tell me, is it plus or minus? This VC is plus or minus? these things you have done in A-level physics also, okay? Yes, very good. It is minus, no? Because voltage difference is in this direction, okay? The voltage difference is in this direction. Now you are going this way, in this direction, other direction. So that voltage will be definitely a minus voltage. So it will be minus VC. Okay, that is minus VC, that is equal to 0. Okay, okay, okay. So that is how this minus and plus value are changing. Okay, so one student asked the question how this minus and plus will be there. So it is depend on the direction you consider always. Okay, so this is one equation. You need to remove this IC and you need to remove this VC. You need to keep this I. Okay, so another. The equation also I can write. Okay, maybe I can apply the Kirchhoff law in this way. Okay, so this voltage at that time I'm coming on this way, no? Okay, so again this will be minus value because this direction I am considering. Okay, so it is minus VC. So this is plus IC2, IC2. That is the voltage difference. This one plus simple I 2A. That is also 0. Okay, that is also 0. Okay, now so you need to get rid of this IC and VC. Okay, but I think another equation should be there, no? Otherwise you can't get rid of. Okay, okay, maybe you can apply the Kirchhoff voltage to this whole one. Okay, so at that time this current is flowing in this way, that is IC minus I. So it will be minus value minus IC minus I into 6. That is the voltage across this resistor. And this will be plus 12R. That is also 0. Okay. Okay, now what you need to do? Okay, you have three equation. You have three equation. Okay. uh, no, actually, this equation will come when you add or subtract this from this one. No? Okay, so this equation is not important. මේ equation එක වැඩක් නැහැ. මේ පොඩි දෙකට Kirchhoff law දාලා මේ ලොකු එකට දැම්මට වැඩක් නැහැ. මොකද මේ දෙක එකතු කරොත් හරි අඩු කරොත් හරි අර equation එක තමයි එන්නේ. ඒතකොට මේක වෙනම equation එකක් නෙවෙයි. Okay, this is not a separate equation. So you can get this equation by subtracting or adding these two equations. If this is equation is A, if this equation is A and if this equation is B, okay, if you add or subtract, you will get this equation. Okay, that is for the total round. Okay, so this equation is not usable. Okay, okay. So you have to write another equation. So there is another equation that is related between VC and IC. What is that one? So you know that IC is the capacitor discharging current. Okay, so discharging current you can write it as IC. Okay, so you can write as IC. Okay, it is a discharging current, so it will be minus IC. It is equal to C into D VC dt. So you have to consider this one. Okay, this one you can get. Okay, so So instead of IC, you can apply this way, this one. Okay. Instead of IC, you can apply this terms. So it will be minus. It will be minus. Okay. Okay. So if I subtract this one from this one, this VC cancel out. Okay. This ICUT also cancel out. Okay. So I will have this one plus this one. This one minus this one. No? Okay. So that is this equation. That is this equation. Okay. So I will have IC minus simple I into 6. This one minus this one. Okay. So VC cancel out. This one cancel out. This will be minus I12. Minus I12. That is equal to 0. Okay. So I can get 6IC minus 6 simple I minus 12I is equal to 0. So IC is equal to 6 plus 12, 18. 18 divided by 6 is 3I. Okay. So IC is equal to 3I. I can write like this. Okay. IC is equal to 3I. Okay. Okay. So now you can write like this. Okay. IC is equal to 3I. No. Okay. So you can consider one of this equation. Okay. You can consider one of this equation. I will consider this one. Okay. So that is the second one, this one. Okay. You can get any equation. Okay. So one that is IC2. 2 is the resistor. IC2 plus I2L. Minus VC, I will put, so okay, I will write the minus VC is here, that is equal to 0. Okay. Now, IC is equal to 3I, no? Okay. So instead of this IC, I can put 3I here. Okay. So it has 3I plus 12I, that is 15I, minus VC is equal to 0. Okay. So do you have a way to remove this VC? How to remove this VC? Okay. So that is, you know that VC is the voltage across the capacitor. Actually, it is a function of time. Okay. So it is the integration of IC, that is the current. So that is minus, okay, because it is discharging. Minus ICT dt. Okay. Dt. And there is a initial voltage. Okay. There should be an initial voltage. So you have to find that initial voltage here. Okay. Let's say that it is V0 or something. Initial voltage should be there. So that is V naught. Okay. The initial voltage is V naught. Okay. So that is the initial condition. Okay. That is the initial condition. Okay. That is the initial condition. Okay. Uh, so VCT is equal to ICT plus DT plus there should be an initial voltage that is V naught. Okay. Now ICT is equal to again 3I know. Okay. So instead of ICT, you can add C3I here. So you will have VCT integration of minus 3I dt plus V naught. Okay. Now what you need to do? You can apply this value here. Okay, this value here. VC because we need to remove the because we need to remove the VC. Okay, then you will have 15I minus minus uh, minus VC means this one, no? Integration of minus 3I dt. So minus again it is multiplied by this V naught minus, so it will be minus V naught, that is 0. Okay, this minus minus, it will be plus. Okay, now you can get the differential equation, no? How? Okay, now you need to get rid of this integration. For that one, you need to get the differentiation. So you will have 15 di dt plus, because this minus here minus and minus, so it will be plus 3I. This value is cancelled, the integration is cancelled, and this is a constant, so it will be 0, that is equal to 0. Okay, so this is the differential equation. This is the differential equation for find I. Now you have to solve this differential equation. So you can solve this by variable separation. Variable separation. So you will have the value just like this. Okay. Some e to the power minus t plus something. This kind of minus t into something. This kind of IT you will get. Okay. So no need to solve this one. The separation variable easily solve. You can easily solve this one. But at this time, no need. Okay. So this is how you get the value. Hello. 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 Okay. So this is how. Okay. So so I think it is okay. No, it is not much difficult. So anyway, this if you couldn't get this differential equation, maybe some mistake may be there, I don't know. Okay, maybe some plus or minus value may be change. Check it when you are doing it. Okay, if you have any problem, please send me at least WhatsApp message. Okay, this is my WhatsApp number. Okay, if you have any problem, please send me a WhatsApp message. Okay, so I think this is okay. Okay, we haven't do any mistake. Okay, so anyway, if you write these three equation and if you try to get this up to some level, so you can get considerable mark. Okay, so don't worry. Okay, so this way you have to get the differential equation. Okay, okay. Now I think it is enough. Okay, and also you can, as a homework, you can do keep this source, and once you close this, consider the transient state and find the I again. Okay, so when the source is there, find the I at the transient state. Okay, at the transient state, do it as a homework. Okay, if you have any problem, please let me know. Okay, now we will move to the S domain question. Okay, so because you can get very easily around 15 marks. Okay, very easy one. Okay, so it is like this. Okay, what you need to do, what you need to keep remember is, if it is an inductor, capacitor, capacitor resistance is R. If it is a capacitor, it resistance, it is referred as uh, actually reactance. Okay, it is referred as reactance. We can write it as 1 over Cs. Okay, and if it is an inductor, it is Ls. This is what you need to remember. This is simple R. This is 1 over Cs. This is 1 Ls. Okay. Now, okay. Now, if you are given a circuit, for example, okay, let's say that you are given a circuit like this. This is an inductor, this is a resistor, and this is a capacitor like this. And you have a source here. You have a source here. Okay. So this resistance, this is an inductor. So you can write it as Ls. This is 1 over Cs. Okay. So you can use you can consider these are resistance. Okay. These are called reactance. Okay. Actually, these are complex resistance. Okay. Now don't worry about this complex resistance. Okay. So that is it referred as reactance. Okay. This is referred as reactance. Okay. So you can apply the Kirchhoff law like this. Okay. For example, you will ask to find like this. Okay. Uh, let's say that this source voltage is uh, uh, Vs or something. Okay, this is the source voltage. Okay, and you will ask to find, uh, let's say that this voltage is V1. Okay, so maybe you will ask to find V1s. Okay, let's say that this is Vs. Okay, because these are in complex domain, and this is Vs. So maybe you will ask to find V1 S divided by Vs. Okay, these are referred as transfer function. We will see it later. Okay, transfer function, because in DSP, okay, in signal and system, in DSP and in control system, you will learn this. Okay, you will learn this. Okay, you will learn this. What is this transfer function and what is the use of it? Okay, now we are not going to talk about it. Okay. So you will learn these things. Okay. So now we will see how to get this kind of transfer function. Okay. These are normally referred as transfer function. Okay. So you need to find the voltage across this one. So how to find it? So very easy. So this has a current I. Okay. There is a current flowing through this one I1. There is a current flowing through this I2. Okay. So I is equal to I1 plus I2. Okay, I1 plus I2. Okay, so this V1 means the the current through the capacitor. Okay, now you can consider this as a resistor. Okay, so you can write V1 as I1. Okay, because this is I1. Okay, I1, and this I1 is flowing through the capacitor also. I1 1 over Cs. You can directly use that one. That is the V1. Okay. And also this one also V1. So you can write this as V1 as I2 Ls. So just you can consider this as a resistance. Right? Make a resistance එකක් විදිහටම සලකලා දාන්න පුළුවන්. හරි? Okay. So it is very easy. Okay. Now you need to find V1 Vs. So you need to remove this I1 and I2 somehow. For that one, you can write, you can get, maybe you can get another relationship between I2 and I1. This is I1, okay? If you apply the Kirchhoff voltage in this direction, in this loop, within this loop, okay? Let's see that, okay? So this is I1R. I'm applying the Kirchhoff voltage law within this loop, okay? So it will be I1R plus, okay? Now the current is flowing in this direction. So that is that is again I1 1 over CS, I1 1 over CS, and this is so this current is flow, this is marking here, I2 is flowing in this way, but we are applying the Kirchhoff flow in this way. So it will be minus. So it will be minus I2 LS. Okay. So you can get the relationship between I1 and I2. That is I1 R plus 1 CS is equal to I2 into LS. Okay. So now very easily you can find, no? Okay. So you can see that uh, uh, so you can see that this I1 is equal to I2 LS. Okay. I2 LS. Then මේකේ දැන් මොකක්ද ඇත්තටම value එක කාට හරි කියන්න පුළුවන්ද what is V1 is divided by Vs? Can anyone tell what is the, you no need to actually this equation, okay? Without the equation you can tell what is the value of, so I ask you to find V1 is divided by V2s. I told you that, no, this resistor is there. Okay, I forgot that resistor, no? Okay, okay. No, yeah, sorry. You can directly tell that. What is that? Hmm? It is somewhat like this. No, actually, you no need to write this equation. Okay. So it is somewhat like this. No, there is a inductor. Okay. There is a capacitor, and there is a resistor. Sorry, uh, this one. Okay. And this voltage is given. That is Vs. Vs. You have to find this voltage. V1 is. Okay. So you can see that. Okay. So actually, if you solve this equation, you will get the same answer, but very easily you can get this. How? Okay. So the voltage between this terminal and this terminal is Vs. Okay. So that is Vs. Okay. And the voltage of this one is, it is somewhat like this, no? This is Vs. This is the R, and this is the capacitor like this. Okay. So this within this one, that is the V1. Yes. So what is this value? Okay. So using the voltage dividing techniques, you can directly write this V1s is equal to Vs into this resistance is 1 over Cs, 1 over Cs divided by R plus 1 over Cs. This is the voltage divider. Okay. So then V1 is into Vs is equal to so this is what you need to find. Okay. V1 is Vs is equal to uh, uh, this one will be 1 over Cs into the Cs will go up, Cs divided by RCS plus 1, no? So the CS cancel. So we will have 1 over RCS plus 1. Okay. So this is the answer. Okay. Actually, you no need to write this equation. Okay. Okay. If you write this equation and you can say that, no? So you can find you can write another equation for the V. Okay. So V is equal to Vs is equal to I2 LS. Vs is equal to I2 LS. Then V1 is equal to V1 is equal to V1 is equal to I1 1 over CS. Okay. Vs is equal to I2 LS. V1 is equal to I1 LS. Okay. So so here you can find the I1 divided by I2. Okay. I1 divided by I2 you can find here. Okay, that is LS divided by using this one you can find I1 divided by I2, that is LS divided by RCS plus 1. Okay. And if you get the division of these two equation, okay, so that you will have again V1 is Vs is equal to 1 over CS I1 divided by LS. Okay. So you will have I1 divided by I2. So you can apply this value here. Okay. You can apply this value here. Okay. So this LS and that LS cancel out. Okay. So you will get this value RCS plus 1. Okay. 1 over RCS plus 1. Okay. So in this way you can, anyway you can write. Okay. So this is the way. Okay. So sometime maybe you will ask to find, for example, maybe you will ask to find I1 is divided by Vs, this value. Okay. So you have to find this value. This is also a transfer function. You have to find this value. You can have S terms and R and L and C terms. Okay. So using the equation, you can find that one. Okay. Okay. So write the equation and you need to get the relationship between RL, C and S. That is what you have to do. Okay. Is it okay? Did you get the understanding? Okay, we will do this question also. Okay. So just find this one. Okay. Okay. So this is I will modify this. Okay, because you are not the current source will not be there. Okay. So I will remove this current source. Okay. I will write the equation again. Okay. Like this. Okay. So you have, let's say, let's put the inductor here. Inductor and capacitor. Okay. And there is another resistor and capacitor and resistor and this is the voltage. This is the voltage source. Okay. This is the voltage source. Okay. Then you are asked to find this one. Okay. V2 is IS1. What is IS1? Okay, IS1 means inductor. Okay. So let's say that this voltage is IL. Okay, IL. Okay, and this voltage is Vs. Okay, this voltage is Vs. Okay, so you are asked to find ILS divided by Vs. Okay, this is a transfer function. It is given as a transfer function H1s. Okay, so you have to find ILS divided by VLS. Okay, so how you do? Let's say that just put some mark here. Uh, okay, some value here, not the numerical value, just unknown value. Let's say that this is C1, this is C2, this is R1, this is R2. Okay. So just try to write some equation, and sometime maybe we can't find because I just think and give you this circuit, but in the exam circuit, I just work on that one. Okay. So definitely you will get the relationship. Okay. But we will see how to get, how to approach this kind of circuits. Okay. So, so you can write this resistance as 1 over C2S, this resistance as 1 over C2S, this resistance as LS. හරි. එතකොට මේවා මේ R1, R2, R3 වගේ තමයි යා. එලින්ම ගන්න පුළුවන් ඔය කට්ටියට resistance විදියට. You can directly consider this as resistance. Okay. No need to consider any uh, transient state or other state. Okay. But once you find this S, you have to, if you, when you are converting this S into time domain, again you have to do the integration and differentiation. Okay. But when we are analyzing this in the S domain, you no need to do any integration or differentiation. Okay. So try to find this ILS, VS. I give you five minutes. No, I will do this. Okay. Just try to do this by yourself later. Okay. Okay. I will write some equation. Okay. So this is C1, this is C2. Okay. So source is Vs. Okay. Now let's say that this current, this is I. Okay. So now one current is flowing through this one. Let's say that is I1. So this will be I minus I1. Okay. And let's say that this is IL. So this will be I1 minus IL. Now you have to apply the Kirchhoff law and Ohm's law. Okay. So so you can apply the Ohm's law here maybe. Okay, in this law. Okay. If we apply the Ohm's law in this law, you will get this is the source. Okay, source Vs is equal to this current is I R2, that is the current to R2. Okay, and the current to this C2 is I minus I12. Okay, so it will be in this direction. Okay, so same direction, the current is in this direction, so it will be plus I minus I1 C2. Okay, that is the current. Okay, then you can apply the Kirchhoff law in this law. Okay, in this law. So so the voltage across this one I1 R1. Okay, voltage across this will be 1 over C2, C1S, this is C1, C1S, C1S, I1 minus IL, I1 minus IL, and this is, so in this direction, I'm going in this direction, the current is flowing in this direction, I minus I1 is in this direction. So it will be minus 1 over C2S, I minus I1. This is equal to 0. This is another equation. Another equation you can write in this loop. Okay. So if I write in that loop, IL LS, that is the voltage across the inductor in S domain. And this one is again, the current is flowing in this direction, I1 minus IL. I am applying the Kirchhoff law in this direction. So this will be minus 1 over C1S I1 minus IL equal to 0. Okay. So these are the equation 1, 2, 3. Okay. These are the equation we can write. Okay. These are the equation we can write. Okay. So there are three loops. No. So you can write 3 equation for the 3 loops. Okay. Then using this equation, you need to get this value. Okay. So you need to try to remove this I and I1, then you can find the relationship between IL and V. Okay. So try to do this by yourself. That is a mathematics work, not the circuit work. Okay. So this is how we apply the Kirchhoff law in S domain. So that is very easy. Okay. It is just like a resistive circuit. Okay. The only difference is if there is an inductor resistance will be LS. If it is a capacitor, that is 1 over C1S. Okay. So you can apply the Kirchhoff law for a normal resistive, just like a normal resistive network. The resistor are R, no change. If there is an inductor, resistance will be LS. If there is a capacitor, the capacitance will be 1 over 6. Okay. So these are the equation you can write. Okay. Okay. Do you have any problem of applying the Kirchhoff law? I think this one it is around 15 marks. Okay. 10 to 15 marks. You can get maximum 15 marks, but I think you can get the total 50 marks. Actually, if you write this equation, I can give you almost full mark. Okay. If you haven't find this one, but if you have written this one, I can given you around 80% of the full mark, 80 to 85% for the full mark. Then you can get the considerable marks, at least 10 marks you can get, 10 out of 50. Okay. Okay. So do you have any problem? Please try to do this by yourself. Okay. Okay. Try to do this by yourself. This kind of questions are there in notes. Okay. So I have done some question. The same question you will have in that note with the answer. So you can do them. To have a practice, you can do them. If you have any problem, you can send me a message. Okay. Then I can help. Is it okay? Shall we wind up? Okay, if you don't have question, we will wind up, okay? Hope you can write the exam well, okay? I will upload this recorded session. Okay, okay, we will wind up. No. You no need to perform the Laplace transform, okay? The inverse Laplace transform you no need to perform. Just find the transfer function with the S domain. S domain transfer function, that is what you need to find. S domain transfer function means the ratio between the current or voltage, maybe current, maybe two currents, or maybe two voltage. So what you have to do is just write the equations and find the relationship. Okay. Are there any question? තේරුණා නේද කියප එක? ආයි Laplace transform, inverse transform දාලා හොයන්න ඕනේ නැහැ. හරි. Laplace S domain එකේම ඔය කට්ටියට equation ටික ලියලා මොකක් හරි එක්ක current එකකුයි voltage එක ratio එකක් එහෙම නැත්නම් voltage දෙක ratio එකක් එහෙම නැත්නම් current දෙක ratio එකක් වගේ හොයන්න දෙයි. එතකොට ඒක හොයන්න තියෙනවා දැන් අපි හදපු වාගේ. අපි හදුවා ඉස්සෙල්ලා voltage දෙක ratio එකක් දැන් අර current එකයි voltage ratio එකකුයි හදුවේ. අන්න ඒ වගේ. හරිද? Shall we wind up? Okay, we will wind up, okay?